Good afternoon to everyone. We will start our discussions on the week 8 NPTEL course content, Smart Grid Basics to Advanced Technology. This is Adyasha Sahoo, a PhD scholar from Department of Electrical Engineering, IIT Roorkee. In this week 8, we will start with the PMUs and then see the mathematical model for the optimal placement of these PMUs in the system, ensuring the observability of the system. And we will also go through the various algorithms or methods used to solve the model. Thereafter, we will move towards our discussion on cyber attacks, different types of cyber attacks, and detection techniques. Thereafter, then we will also have a look at virtual inertia and various demand side management techniques that are being discussed widely. With this, let us start with the PMUs. So, we have seen in the earlier lectures also, these PMUs are the crucial components of the smart grid because they are the devices which are initially giving us or providing us with the data in the field, actual field. And basically, with this available data in the real time, we are able to perform various power system studies, and also we are able to take correct control actions at the right time for enhanced system reliability, stability, and resiliency. So basically, we see that these PMUs basically they are used for the real-time monitoring of our system, and they provide with us the phasors, both the voltage and current magnitude and the angles at various locations in the grid. So, at various geographical locations across the grid, we can have the information of the phasors of the voltage and the current. So, these are basically crucial for understanding the state of the system. So, basically, the state of a power system. Basically, we have two states, that is voltage magnitude V mod V and the voltage angle delta. Using these states, basically we can comment on the stability of the system. Further, we can also compute various other electrical attributes such as power flow through the lines and various other things, various other studies. These are the starting points for those studies. So, hence, by understanding the state of the system, the operators can basically detect the disturbances in the system, and then they can also take the control actions or respond to these disturbances to avoid the grid instability. So, how this is done is with the help of wide area situational awareness. This also we have seen previously. Basically, since the PMUs are deployed across various diverse geographical locations, so the grid operators can visualize the state of the complete grid using various visualization tools such as your charts, and there will be display screens, large display screens and charts. Basically, there will be display the geographical or the topology of the grid. So it will be displayed in the screen, and then the entire system can be visualized in the screen. And basically, if there are any disturbances such as oscillations between two control areas or sudden dip or rise in voltage and the frequency. Yeah, the disturbances in the grid, the voltage and frequency deviations and oscillations. So those all can be visualized in the screens. There may be alarms that are beeping up or some red signals, red flags that are shown at that, let's say at this particular location, the frequency is dipping very fast. So by visualizing this the system operator then can basically take the various corrective actions to avoid the instability. Then the next important thing is this PMU data are time synchronized with the GPS to ensure that the various measurements across all the locations are basically in synchronism. So this is crucial for recalculating the phasor angles and differences at other bus locations. And these are further used in the various power flow and system stability studies. So if you don't have the correct data, then these studies may not work accurately and you may give wrong control actions. Then next thing is good evening. Hi. The next thing is enhanced grid
Hello, good evening, sir.
good evening. Hello, actually. I'm Adyasha. So next thing is your enhanced grid stability. Basically, as I said, the PMUs will provide you the data that are required to carry various power system stability studies, various dynamic studies, and with these studies, the operator can take the various preventive and corrective actions to maintain the grid's stability. And what are these control actions? Basically, what is happening is through the PMUs, you are getting the information of the phasors of voltage and current. And this data is basically used for power system studies such as your state estimation, various power flow studies, stability studies like your dynamic stability. And basically, these studies will provide the actions, control actions. So these control actions can be preventive or corrective. So these control actions will basically ensure the stability of the system. Yeah, so as I said, these PMUs are giving the data for the power system analysis, such as your state estimation, contingency, transient stability studies. And these analysis help in the planning and optimizing the grid operations or actions, basically. Then next is they also facilitate in the integration of the RES because they are allowing. Oh, my voice is not audible. Can you speak like I'll check if you are audible or not. Is it audible now? Hello. I think you can just type in the chat box and let me know that if the voice is audible now or not. Can you speak?
Hello,
Um,
hello.
I can hear you, but I think there is issue with mine. So let me. What can I do? Oh, sorry. Is it audible now? I think it is audible now.
Yeah, it is now audible.
Thank you for making me aware of it.
Thank you.
So basically, I'll just repeat what we were discussing. So this week we'll start with the PMUs and their optimal location of the PMUs, the model formulation, and then we'll see the various methods to solve the optimal PMU placement problem. Starting with the PMUs, we have seen in the previous weeks also. The PMUs are nothing but they are giving us, providing us with the data in the field. And what data they are giving us? They are giving us the phasor of the voltage and the current. And using these data is very important for us because it is helping us to carry out various other power system studies, such as your state estimation, your power flow, your contingency analysis, your stability studies. And by performing these studies, then we can basically assess the stability of the system, the health of the system, and if the system is unstable, if we detect that the system is not stable, we can take the various control actions to basically bring the system back to the steady state or the normal operating state of the system. So the key features are basically that the data that the PMUs are providing us across the geographical locations at different geographical locations, they are all time synchronized with the GPS, and hence basically we can use them for the power system studies. Just bear with me. I think the power went off. I'll reconnect my Wi-Fi.
Hello.
Hello. Actually, I lost the Wi-Fi connection. I'll just reshare
Yeah.
my screen.
Okay.
Just bear with me for a minute. Okay, so moving on, then what are the basically challenges for installation of these PMUs across our network? So firstly, we face the budget constraints because primarily these PMUs are not very cheap devices. Uh, Initially, basically the PMUs itself are expensive devices. So we need to assess at what location we want the installation of this PMUs. Secondly, also these PMUs require a reliable communication infrastructure to basically transmit the data to the control center, and also we need time synchronization with the GPS. So all this require a very good communication infrastructure to be there, which is not the case currently, which is not basically the scenario currently. We don't have such infrastructures at each location, at all locations, and hence we need to upgrade the communication infrastructure also. So that will also again add up to the cost of the PMU device. Secondly, similarly, we require also various other sensors and equipment such as your voltage transformers and other things, adding to the cost of the PMU deployment. Then the PMUs are basically sensing or able to provide with us a very high frequency data, and hence we required advanced or very good data management systems, and also we need a good storage system available with us to store this high resolution data that is coming from the PMUs, and to handle these large volumes of data in a real time application may also be a challenge for us. So basically, the grid operators they have to basically do the if else analysis and see that there will be a trade-off between the observability of the system and the cost that comes with it due to the budget. So due to this, you can see the map of the our country, and here, basically, if you see, you have one central PDC here, green one, that is at the New Delhi, where you have the NLDC with a. Then you have various local PDCs by the black stars. You can see here uh, deployed across this. And then you have regional PDCs. So the regional, you can see this is the southern, this is the eastern one, the western one. Then I think yeah, northeast also you have one, and the north you have already your central PDC, and then you have various upcoming PMU pilot projects coming in the next phase. So what we do due to this budget constraint, basically the grid operators will prioritize the installation of the PMUs at the key substations or which are important substations according to the history of the grid. And hence, we have first installed the PMUs at the five, basically, we have regions, right, with us. That is your northern, western, eastern, northeastern, and southern. And once this was done, then in the next phase, we are going for installation of other PMUs distributed across the country. So we do the phased deployment of the PMUs.
This PMU and the RTU is
PMUs basically, you need the PMU and you need the RTUs for managing the data that is coming from the PMUs and all. So they will add to the infrastructure once again, where you will have the PDCs and everything, phase data concentrators and
different.
all. Then we have. this mathematical model for basically assessing the optimal location for this PMUs. So here you see this, you what data you need for the model. First, you need the network data, basically the information or the location, that how many buses you have, what lines are connected between the buses, what is the resistance of those lines. So that network data you need to feed to the optimization model. And you also need to run the DC optimal power flow model and give it to the optimization model. We'll see it how in the next slide. Then the objective of this optimization model is basically cost minimization. So, and we considering the objective is cost minimization subject to various constraints, and these constraints are primarily your state estimation constraints, your observability constraints, and so this is the model, optimization model. The input or the data required is the network data, and the output that you get from is the location of the PMU, location of PMU in the network. So any optimization basically problem is will have an objective function. So the objective function is in the form of can be basically minimizing the function fx or maximizing some function fx, and with that you will have some constraints. Now the constraints can be majorly divided into two categories, that is your equality and inequality constraints. Uh, so in the equality constraints, you have basically from the power system point of view, can you give me an example of a equality constraint? Voltage level, basically we want that the voltage remains within some minimum and maximum limits. So if we talk about per unit, we say that the voltage may lie between zero point 0.9 to 1.1 per unit. So this will give you a region, right? So it is a type of inequality constraint. In the equality constraint, you have the equality operator that some operations is equal to something. So your power balance equations to basically ensure that your summation of the generation, P generation, is must match the load demand plus the losses in the system. So this should exactly match. So this is the type of equality constraint. And in the inequality constraint, you can have your these voltage constraints that you said, or it can be the limit on the output of the generator, because a generator can produce active power within the installed capacity, within its installed capacity, that is P max. Similarly, you can have limits on Q gen also, on the voltage, as you said, on the angle also. Then you can also have inequality constraints for the power flow through the lines. Basically, this Pij between power flowing between the bus I and J should be within its thermal limit or voltage stability limit, whichever limit you are considering, given by Pij max minus Pij max. So why is that? Let's say there is a line connecting between this bus I and J, and the power flow through this line is Pij. and the thermal limit is Pij max, then which of this constraint is correct between 1 and 2, or between A and Y?
Actually, second one, because sometimes no load, then second B constraint is okay.
Okay, but in the practical power system, can you always ensure that the power is flowing from I to J? Cannot the power flow from J to I?
Yeah, possible.
Possible, right?
Yes,
So that will depend basically on the voltage at these buses, V angle, Vi angle,
yes.
delta I.
All
Hmm.
and yes.
Yes. So basically, sometimes it may happen that the power is flowing from I to J and sometimes from J to I. That means due to this
Yes,
bidirectional power flow, you need to have the inequality constraints in the both the directions. So this is, let's say, from I to J, and this will ensure between J to I. So hence A is correct. So this is how a optimization problem looks like. So it will have some objective function. It will have some constraints. So if we visualize this, basically what we are doing with this, let's say this is your, let's say you have a two variable problem. That means there is only two variables in the optimization problem. Let's say those are X and Y. So since you have only two variables, so that is your surface looks like this. Now let's say the constraints that you have is X will lie between 0 to 5 and your X is equal to Y. So these are your two constraints and you want to maximize, let's say, X. Let's say you want to maximize X only. So how this works is basically in the initially, if you don't have anything, your region is basically this infinite two-dimensional space from 0 to infinity, minus infinity to plus infinity for X and similarly for Y. Now by adding this constraint 1, what we do is we cut off some of this subspace. So we are telling that X can only vary from 0 to 5. So let's say 5 is somewhat here. So by doing this, what we are doing is basically we are chopping off some of the region. So we are saying that X cannot go beyond 5. So this is not possible, this region. Now the next constraint that you have is, and also, so that is X is less than 5. Similarly, you see that X is greater than 0. So this is 0. That means this complete region is also cut off where X is negative. That completes your equation 1. And in the second equation, you are saying that X is equal to Y. So X equal to Y will give you a straight line passing through origin. This is x equal to y. Now, this is the equality constraint. That means your solution, whatever is the solution, can lie uh, only on this line. So the rest of the regions are again cut off. This is also cut off. This is also cut off. This is also cut off. So after adding both the constraints, your available search space is only this line between x equal to y between 0 to 5. Now that you have added both the constraints, now you look at the objective. So your objective is to maximize the x. So on this straight line, if you want to maximize x, what will be the solution? You see here x will be 0, then x will be 1, 2, 3, 4, 5. X can go from 0 to 5. So these are all your feasible points. So among all these points, where will be x maximum? Yes. So this point basically your solution is when x equal to 5. And when x equal to 5, what will be the value of y?
Y also 5.
Yes, because we have the constraint x equal to y. So your optimal solution for this problem is likewise. So basically, with the help of your inequality constraints, you are chopping off the feasible region. In the equality constraint, basically, it will ensure that the solution must lie on that specific line. And then when you have basically come up with the feasible points for the considering all the constraints, then you look at your optimal solution depending upon the objective. So this economic dispatch versus OPF. So these are two types of optimization problems carried out in the power systems. So in the economic dispatch, our objective is to minimize the cost of generation, basically minimize the cost of power generation. So let's say you have two generators, then it will be C1, which will be a function of Pg1 plus C2 times Pg2. And subject to the constraint we consider here is that the Pg1 plus Pg2 should be equal to the load demand, basically your power balance. And next we consider that the Pg1 and Pg2 must be within their limits, maximum and minimum limit. So the solution that we get here is basically the dispatch schedule of the generators, considering economics to meet the load. So if we add economic dispatch plus the line constraints, basically transmission line constraints, so that will give you the OPF. So economic dispatch is not considering your network, no network. That means no transmission lines are considered here. So economic dispatch plus your network considerations, power flow considerations basically. So that will give you the optimal power flow problem. So here we can have variety of optimization objective functions. So it can be cost minimization depending upon your application. It can be loss minimization. It can be basically minimize the voltage deviation, or it can be to minimize the emissions, carbon emissions. So these are, or you can also try to maximize the profits. So these are some example of the objective functions that you can consider for the optimal power flow. Subject to, here you have, as usual, your power balance equation. But in this power balance, we will consider the network. So how we will do that? Let's say this is a bus I, and you have a generator here, PGI. You have a load here, PDI. You have a line, and also you have a line K here. So power balance at bus I, basically we see the direction. So we see which all powers are basically injected into this bus. That means that are going into the bus. So that is nothing but your PGI plus PKI. So that should be exactly equal to the power that is going out from the bus, taking out. So that is your PDI plus PIJ. So that is your power balance for bus I. So here we have considered the PIJ and PKI, which we were earlier not considering in the economic. Then along with this, as usual, you will have your power flow line constraints like your limits on PG, limits on power flowing through the PIJ. And depending upon your application, you can have other sets of constraints. Like in optimal PMA placement problem, you have your state of estimation constraint, observability constraints. We will see those next. Now, in the linearized OPF, basically what we do, DC OPF, what we do, we basically consider only the active power. We consider that there is no reactive power or there is no voltage for simplifying our model. So you see here the objective function is to minimize the cost. So you have total ng number of generators. So 1, 2, ng number of generators, and their sum you are taking to minimize the cost. And what is your constraints here? Basically, you are considering your power balance, which will be your equality constraint. You have your line power flow limit or inequality constraint, or power generation, again, inequality. So this is your power balance for all bus I. So it is a generalized power balance equation for a system which has, let's say, I buses So from here you can see the system has I number of buses, ng number of generators. Then you ensure that the power flow, this is nothing but your Pij is delta I minus delta j divided by the reactance of the line Xij. So Pij, if you place it here, that should be within its min-max limit. So this is your line limit, and this is your power generation limit within it. So here for all I belongs to Ng basically. Now we will see that why we need this DCOPF model to be incorporated into the optimal PMU placement model. So you see, for the optimal PMU placement problem, your objective function is to minimize the PMU installation cost. So for that, we are minimizing the objective function A. For here you see I is from 1 to NB. So let's say you have a system with NB buses. So how many candidate locations you have for your PMU? So PMU can be installed at NB bus locations. So let's say you have a 6 bus system. So it is having 6 locations, 6 buses basically. So you have 6 candidate locations for installing the PMUs. So your PMU has to be installed at one or more locations of the 6 bus system. So this X is basically represent XI is telling that whether a PMU is placed at that bus or not. So if I say X1 equal to 1, that means I have a PMU installed at bus 1. If I say X2 equal to 0, that implies that there is no PMU at bus number 2. Similarly, if I say X3 is 0, again no PMU at 3, no PMU at 4, 5 also, we let's say there is no PMU, and at 6 is 1. So if I get a solution like this, so from this I can inform that my PMUs are located at bus 1 and bus 6, and rest of locations I have no PMU. So this X are basically binary decisions variable that are telling us whether you have the PMU installed at the location or not. Okay. So here we were trying to minimize the cost of installation of this PMU. That is your objective function. Now we are basically considering the state estimation constraints. So here you see uh, this constraint. Let's say we'll see at this first constraint. So we will break it down. Let's say if xi is 1, then what will happen to this constraint? So this will be 1, this will be 1, this is 1, and this is 1. So this constraint will be reduced to Pij true 1 minus epsilon times PMU, and this will basically be 0. 1 minus 1 will be 0. So that will go out is less than equal to Pij, and similarly here you will have Pij true into 1 plus epsilon PMU. Now if x is 0, so if x is 0, basically this will reduce to Pij min less than equal to Pij less than equal to Pij max. Similarly, this also will go for the locations of your demand. This was for your generation, this was for your load demand. And next you consider that the voltage angle, basically delta, is lying between pi by 2 to minus pi by 2. And again, here also you are calculating that the difference is lying between the acceptable limit epsilon here. Then next, basically, so this true values basically you get from your DCA pair. So what about next is your observability constraints. So why you need this observability constraint is because uh, we want to install the minimum number of PMUs with which your system can be observable. What that means is, let's say you have a 30 bus system, and let's say you install only one PMU. So using this data, then what we do next is we do the state estimation to find the voltage at the all location. But now, since for the 30 bus system, using only one PMU, you have the data at only one bus. So utilizing this information, you cannot get the information at other 29 buses. So you need to decide minimum number of PMUs to be installed such that the complete network is observable. So what this means that you need to find out that how many minimum PMUs, let's say 3 or 4 or 5 PMUs. Let's say you find that by installing 5 PMUs, you can get the information of all the rest 25 buses. Then we say that the complete system is observable. So that is ensured by this constraint summation xi greater than equal to 1. So we'll see how this constraint ensures the observability in the next slide. So what basically laws that we use, three laws that we use are, firstly, that if you know that the phasors at one bus, at bus I, then you can easily compute the information of the other bus J. So let's say the impedance is Zij. So if you know the information at Vi, then you can calculate Vj as Vi minus Zij Ij. Basically the drop in this line. So hence, if you have information at bus I, then and you have a line connecting between bus ij, then you can also find the information at bus j. Next is if you know the voltage phasors at both the buses I and j, then you can compute the current phasor. So that you know that Iij can be computed as Vi minus Vj divided by Xij. And the next is for your zero current injection buses. That means you do not have any generator or loads connected to it. You have only transmission lines passing through this bus like this way. And for such a bus, if you have the information for the currents at through all the lines but one, so you have three lines here, and if you have the information of the current through two lines, then you can consider you can compute the current flowing through the last line. So because let's say this is I, J, and K. So Kirchhoff's current law says that the summation of the current entering to the bus, incoming current, basically IIJ, is equal to the outgoing current. That is, let's say this is JK1, JK2, so IJK1 plus IJK2. So from these three currents, if you know two of the currents, you can calculate the third. So using these laws, we will now write the observability constraint for this 14 bus system. Just a second.
So,
Hello.
okay.
I'll just reconnect the Wi-Fi for better connectivity. Yes. So let's say for bus one, okay. Uh, so what we write is this x1. So x is basically your binary variable. So x1 plus you see which are the lines connected at bus one. You have two lines, that is your 1, 2 and 1, 5. So x1 plus x5 plus x2, that should be greater than equal 1. So if you remember this constraint, it says for all the buses will write that the summation of this xi's is greater than equal 1. So basically what this means that if you have the information at,
Can you repeat, ma'am? I didn't get.
yes. So basically what we are trying to say that if we have a PMU installed at any of these three locations, then you can have the information from other two locations using these laws. Basically, we first find out the bus. Let's say we are writing for bus one. Then we see what lines are being connected to this bus one. So the two lines are connected here, 1, 2 and 1, 5. So we write x1 for bus one, and then next we write 5 because the line is 1, 5 and the other line is 1, 2. So x2. So for bus one, this will be the observability constraint. Then for the similarly for second bus, if you see how many lines are there here, there are four lines. So they are 1, 2, 2, 5, 2, 4, and 2, 3. So here the constraint will be x1 plus x2 plus x3 plus x4 plus x5 is greater than equal 1. Basically, you find the lines and then you write the bus decision variable location with the lines that is being connected to that bus. Similarly, if for bus 3, you have the lines as 2, 3.
The consent is also being included.
Yes, the concerned bus is also included.
That means if we consider bus S2, then we have to consider bus 2 plus connected lines.
Bus plus the connected line of the other end. Basically, bus
Okay.
one end is fixed. So similarly, for if we see for x3, then we have the lines as 2, 3, 3, 4. Two lines are there. So here it will be x2 plus x3 plus x4 is greater than equal 1. Similarly, how many equations you have to write? You have to write 14 equations for each bus. And that will give you the set of observability constraints for this 14 bus system. So the optimal placement problem will be nothing but minimize the for how many buses are there? 14. So for CI, XI, the candidate locations are from bus 1 to bus 14, subject to your power balance. So this will also be again 14 equations for each bus, then subject to your state estimation constraints. This will be for your generators and loads, and then subject to your observability constraints. So these will be again 14 equations for 14 buses. Then you will have subject to your angle limits between pi by 2 to minus pi by 2. So this will again be 14 for all buses. So hence this will be the typical formulation of optimal pay-view placement problem for a 14 bus system. Once you have then formed this optimization model, you have various techniques to solve this. Before going to the techniques, we will see the results. I think the screen is stuck. Just a second. I'll reshare the screen once again. Wait. Hello, is the screen visible to you? Like, is it moving or is it fixed? Yes. So once we have framed this optimization model, and we'll solve it using various techniques, we'll discuss those later. First, we'll see the result. So the model tells us the optimal locations for this 14 bus is 2, 6, 7, and 9. So by installing PMUs at these 4 bus locations at 2, 6, 7, 9, you can compute the information of the rest buses, and the 14 bus system is completely observable. Let's see what all are remaining. 1, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14. So once you have the information at bus 2, then if you see the network, you can have the information at bus 1 and bus 5, and also 4 and 3. So if you have 2, so you know 1, you know 3, 4, 5. Similarly, next, if you know 6, then you see it is 6. So you know 12, 13, 11. Yes. So 11, 12, 13. Next, you have bus 7. So if you know bus 7, so you know then bus 14. And if you know bus 9, okay, 6 also complete. Yes. What is left? 8 and 10. So if you know 9, you know 4. 4 is already known. You know 10. And for 8, basically, it is connected to this bus 7 through the transformer. So that also information you know. So with this 4 bus locations for the PMU, you can have the information for the rest of the network. Now, what are the techniques to solve the optimization model? So first, you need to basically figure out that what is the type of your optimization problem. So if you have a linear, objective, function, and constraint, so we call it as a LP problem, linear optimization problem type, LP type, linear problem. Then if you have a nonlinear objective plus linear constraint, or you have linear objective plus nonlinear constraint, or you have both nonlinearity in objective function and constraint, so we call it as a nonlinear problem. So by nonlinearity, we means nonlinearity can be of various types, such as your multiplication of variables, or you may have different mathematical functions such as your exponential or trigonometric. So these all add to the nonlinearity of the system. So that is called a NLP type. Now next thing is, if in a LP problem, you also have binary variables. So the variables can be of different types. So variables can be continuous. That means they can take any value, any rational or any rational value between the range. They can be binary. That means they can either be 0 or 1. They can be integer type. That means they can take such as 0, 1, 2, 3, only integer values. Yes. Integer variables are such. So if you have LP with binary or integer variables, then it get converted to a binary or integer variables. We convert it into a mixed integer linear programming type problem. And if in a NLP problem you have binary and or integer variables, so that becomes your mixed integer nonlinear problem, MINLP. So these are the classification of the optimization problems depending upon their types, basically depending upon the objective function, constraints, and variables. So this LP and MILP type are easier problems to solve, and you can guarantee the optimality of the problem. That means when you solve these problems, they have a single optimal point, and hence you know that you have guaranteed optimality with you. But in case of a nonlinear programming, NLP and MINLP type problem, you cannot guarantee the optimality of the solution because they have multiple minimas that you call local minimas or local maximas. So whenever you get the solution, so you cannot always guarantee that you have arrived at the global solution. It may sometimes happen that you stuck in the local solution, and hence these class of optimization problems are difficult to solve using your classical optimization techniques. So LP and MILP guarantee the optimality, whereas your NLP, MINLP, global optimality is not guaranteed. Then the other category. So using this classical optimization technique, basically we have different techniques such as your interior point method, Newton second order method, Newton first order method. So these are mathematical techniques which arrive at the solution. But the meta-heuristic type, here we have algorithms such as your genetic algorithm, uh, then ant colony algorithm, then gray wolf optimization, then your particle swarm optimization. So various algorithms that are inspired by the nature, the way the nature operates basically. So the in the GA where we basically have the concept where that the survival of the fittest, that among various offsprings that are available in the next generation, only the fittest or the smartest one will survive for the next generation to come. And these are iterative algorithms. In PSO, similarly, it is inspired by how the birds are choosing their food, particle swarm optimization. So there you have concepts such as your global best and local best. So iteratively they update depending upon their experiences so that they arrive at the the birds they arrive at their food. So depending upon these algorithms are formulated in such way. So the disadvantage of these meta-heuristic techniques are firstly they are iterative, they do not guarantee the optimality, and you get different solutions for same problem. Whereas the classical techniques they guarantee the optimality. So here if you discuss one by one, so the GA has a disadvantage of long execution time, whereas it is robust and adaptable. And the binary search again, it is time consuming. So integer programming, this is again your classical optimization technique. So it is computationally fast, but the constraints are non-linear. Similarly, various other meta-heuristic techniques such as your BPSO, binary PSO, research and topology. So each are having its advantages and disadvantages. So depending upon your application, you can choose your algorithm, whether you want the solution quickly or you want the solution to provide optimal solution, and you are not bothered about the computational time. That completes the optimal PMU placement problem. The next discussion is on cyber physical systems. So earlier in the system, we had only the physical layer. We did not have communication infrastructures and all. So in the physical layer is basically what consists the actual components of the power system, such as your generators, loads, lines, substations, transformers, and other devices. So those are the physical layer of the system. Now, when we add physical layer, physical, okay, physical layer plus communication. So physical layer plus communication will give you the cyber physical system. And this communication is basically your cyber layer. So here you see you have information passing between all these nodes. So these blue lines are basically the direction of communication. And when you basically superimpose communication with the physical layer, we get a integrated cyber physical network. So here you see the physical layer in the bottommost where you have generation, transmission, distribution, and consumption. Now, the control center where you have your EMS, energy management system, and you have super SCADA system, you have load frequency control, AGC. So all these computations are power system computations are being taken carried out at the control center. So the physical amenities are communicating with the control centers through this communication network. So the information, basically the PMUs will be located at this physical layer, and they will communicate this information to the control center. Then using those data, the control center will do various power system studies, and then it will give the control action back to the physical layer through the communication system. So here you see the data information flow. Basically, your PMU data is gone. Then computations are done here, and the control signal is passed to the physical layer. So the communication can be of different wired or wireless type, as we have seen in the previous lectures also. What are the advantages and disadvantages of this cyber physical system? So basically, this is helping us to advance towards the smart grid era because we can have your substation automation and various smart features. We can have flexible operations, we can have coordinated operation, and we are also able to ensure the security, reliability, and resiliency of the system. And we have two-way info flow of information and power. But the disadvantage is with this cyber physical system is basically malicious control effects. Basically, we'll see how the data can be manipulated by the third party to hamper the system. Then there is network congestion due to all this. There may be communication latencies because we are heavily relying on this communication network. And lastly, we can also face cyber attacks. So the cyber attacks are basically of two types. That is your false data injection FDIA, false data injection attack, and DOS is your denial of service attack. So in the false data injection, what happens is basically the cyber attack. In this type of cyber attack, the attackers will basically manipulate the data that is being sent from the physical layer to the cyber layer, and they will change the actual data, and that will be then the false data will be communicated to the other end. In the denial of service attack, what happens is that they try to interrupt the communication. They want that there will be no communication between the cyber layer and the physical layer. So to interrupt the communication, what they do is maybe they will interrupt the communication layer. So let's say they will cause communication latencies by injecting a large volume of data into the network so that the network will get congested and the communication will be stopped. So that is your denial of service attack. So in the
What is the
false,
expansion
sorry,
what is the expansion what is the expansion of DOS and the FDA?
false data injection attack, and this is your denial of service
False data
injection attack.
injection. Another one.
That is your denial of service.
Okay, thank you.
Okay. So in the false data injection attack, what happens is, as I said, the attacker will basically, you see, you have the physical layer here, you have the control layer here, and there is communication here. So the attacker may interrupt. So let's say the physical layer is communicating X to the control layer. So the attacker will inject some information here and then transform this X to X dash, and this X dash then will be communicated to the control cyber layer basically. So it is basically manipulating the data that is coming. And similarly, also it can happen from your cyber layer to physical layer. So you have the target system. You have basically what are the components here? So the target is the data that is coming from the sensor, such as your SCADA or your industrial control system or your IoT devices, intelligent devices. And these datas are the target of this false FDIA attack. So using this data, the attacker will inject false data to the sensor data that is coming, and it will alter the data packets. And this will then be sent to the other end of the communication. So it will try to mislead, basically mislead between the physical layer and the control layer. Next was the denial of service. So as I said, so in the denial of service, what the attacker wants is basically it wants to interrupt or rupture the communication between the cyber layer and the physical layer. So how it is done? By overwhelming traffic. Basically, you have the communication layer here. It will insert various other data into the communication layer so that the communication burden will be very much high. And due to this excessive volume of data, the communication layer will fail and there will be no communication between the physical layer and the control layer. So they cannot communicate with each other. The next one is the man in the middle attack, MIMA attack that we call. So here basically you have similarly two parties with you, party A and party B, and it will basically again it will position itself in between these two parties and it will basically try to hack the system between them through the Wi-Fi hotspot or any malware, device malware. So first it will position in the network communication network between them. Then it will try to read the information that is being passed between them. So first it will position it here, then it will see what information is being passed. Then after that, it may also try to manipulate the data that is being communicated between them. So interception means it will position itself in the Wi-Fi network. Then it will monitor, means it will see, eavesdrop, it will listen what data is being communicated. Then it will capture the sensitive information that is being passed. Then it will try to modify the data. So without the knowledge, it will so if it will modify the data, so it will feel whether let's say A has communicated X with here, but the information that is being passed here will be X dash. Next is your types of cyber detection techniques. So they can be centralized or they can be distributed. So the distributed methods, they are robust to the noise and the various type of centralized techniques are such as your state estimation and chi-square estimation techniques. So the next we will come to frequency support. So um, what happens whenever there is a frequency mismatch in the system? Let's say the generation is not matching with the load. So the first action that takes place is your inertia. So that happens in the time scale is in the cycles basically. So the rotational energy, since these generators have very heavy rotational part, so the kinetic energy that is stored in these machines, they are used to basically support the frequency. After that, in the order of seconds, we have the primary frequency control. So the primary frequency control is basically your governor action. So basically, you open or close the governor according to whether you have over frequency or under frequency with you. The next takes place is the secondary frequency control in the range of minutes. So here what we do, we try to change the power flow between the tie lines, basically this A and B. And let's say there is a frequency dip or rise in this region A, then the power flow through this tie line AB is changed to support the frequency in area B. So this is your timeline control. Now, in the tertiary frequency control, that happens in your day ahead. So basically, what you do is basically you keep some spinning reserve in the system with you. That means you plan for any contingencies that may take place. And spinning means that your generator is already synchronized, already running and synchronized to the system. That means that since the generators take also some time to start up, like a thermal, they will take time for the boiler to reach certain temperature. So to avoid the time delays, the spinning reserve means that the boiler will be already warm, already to the temperature, required temperature, and it will be also synchronized to the system, and it will be ready to generate power at whenever it will receive any command from the control center by the system operator. It can readily inject power or absorb inject power basically to the system. So it is procured in day ahead, but it is you can say applied in the real time. Then what is this virtual inertia and ancillary support? Now, earlier we had this bulky thermal generators or with us, which had inertia inherently in the machines. But now we have this renewable resources, and this renewable resources do not have these. They are powertronic based sources, right? They don't have heavy machinery equipments with them, so they don't have inherently any inertia with them. So what happens due to this is basically any interruption or any mismatch between the power, then the frequency is basically will shoot up or it will dip down very drastically, or minute changes in the P frequency drastically changes due to the absence of inertia in the system. So what we want is we basically design various control algorithms installed in the converters so that the renewable energy resources they are able to mimic the characteristics of a conventional synchronous generator to provide the inertia virtually, hence the term virtual inertia. So how this energy is stored? Basically, the virtual inertia is the stored energy in the DC link of the renewable energy resources in the converters, and these are then injected into the AC side to maintain the frequency according to the control algorithm that is already fed to the converters. The next we discuss the various demand side management strategies. So here, what basically instead of having a fixed load demand like this, the demand can change its consumption depending upon the state of the grid to help in the system operation. So various types of demand side management strategies are like your peak clipping. So if there is a hmm, uh, there is a peak in the load demand, so this can be removed. This peak energy consumption can be shredded out. That is your peak clipping. In valley filling, what happens whenever there is a low demand, we increase those demands during the period of low demand. Then in load shifting, we have seen that the load is shifted from periods of high demands to low demand. So these loads are shifted to from high demand to low demand. Now, in load conservation, what we do, we decrease the load from the base value. In the load growth, we increase the load from the base value. And in flexible load, again, depending upon the requirement of the grid, the load can follow the grid error. Now, what can be the various demand side management objectives? They can be. maximum utilization of the renewables, maximizing the economic benefit, minimizing power import from the grid, or reducing the peak load demand. Now, next is your single objective versus multi-objective. So, what happens is sometimes, let's say, you have a function such as f1 plus f2 here and f3 plus f4. So, you want to minimize this. You want to minimize this. Now, when can this be considered a single objective function? If that when f1 is decreases, then f2 also decreases, or if f1 increases, then f2 also increases. That means they are in coherence. That can be considered as a single objective function. But if it is such that whenever f1 decreases, the f2 will increase, or by vice versa. If f1 increases, then f2 decreases. That means they basically there is trade-off. Then such kind, if the behavior is such way in the two objective function, then we have to consider the optimization problem as a multi-objective function, because then you need to decide that basically whenever you will try to minimize f3, this f4 will be increased, and if you try to minimize this f4, the f3 will be increased. So there is a trade-off between the optimality that whose objective function you want to decrease. So this comes whenever there is striking difference between the objectives. They are not in coherence. Or if there is, let's say, competition between two players. So to model their competitive behavior, we again go for multi-objective type optimization problem. So in this multi-objective type of optimization problem, what we try to look is for the Pareto optimal solutions. That means you try to look for a region where this F3 and F4 can be balanced. Next is your demand response. So the various objectives that can be considered for demand response are minimization of electricity cost, maximization of welfare, minimization of aggregator power consumption, or minimizing of electricity cost, and various other objectives you can consider for demand response activities. Now, depending upon the control strategy, it can be centralized or decentralized. So, in centralized, the system operator will directly give the command to the demand to basically decrease or increase. But in decentralized control, it will directly not tell to decrease or increase the load demand. Rather, it may increase the price so that the load consumption will decrease. So, that is influencing the demand indirectly is the decentralized control. Now, depending upon price that I said in, so you can have a dynamic price based demand response or incentive or penalty based demand response, such as your time of use, critical peak, peak load pricing, and real time pricing. So, depending upon the condition of the grid, you penalize or incentivize the loads. Now, demand response activities can be again divided into task related or energy related. So, whether you want in the task related that whether you want the frequency or the voltage to improve, and in energy related, you try to basically shift the loads from high energy time to the low energy time. So, this come then we move on to the Q&A. So, which type of variables are used in optimal PMU placement problem? Binary, integer, continuous, binary, and continuous. What will be the answer? Yes, binary and continuous. So we had X, which was binary, and we had other continuous variables such as your PG and delta. Now, sensor attack falls under which category? Yes, correct. False data injection attack. Now, which cyber anomaly detection methods? Why cyber anomaly detection methods are needed? To continue the normal operation of the system, isolate the compromised part, or increase cyber resiliency, or all of the above?
Or
Yes, correct. So, which sources can provide inertia? So, this is your doubly fed induction generator for your wind-based renewables, then energy storage systems, synchronous generator, or all of the above. Yes, synchronous generator can provide. DFIG can also provide. It is also a type of induction machine. Then energy storage can also basically because we have the stored energy there. If you provide the control actions, it can also provide energy to the system. So this will be all of the above.
what is the definition for expression for
Doubly fed induction generator. This is used for wind-based renewable. Yes, induction generator. Yes. So what ancillary service VHG can't provide? Inertia, primary frequency, or voltage, or none of the above. Actually, this voltage virtual synchronous generator, it cannot provide voltage. It cannot also provide inertia or primary frequency control. So it is none of the above.
what is the question again, ma'am?
It is that what actually cannot. The
Can VST means VST means
a virtual synchronous generator.
cannot be provided.
Now, which demand side strategy is more reliable? Load growth, peak clipping, flexible load, or load shifting? In peak clipping, basically, we will shed the load. So we don't want to shed load. It is not positive, right? And load growth, what happens? We cannot also increase the load beyond certain point. So what is flexible is basically load shifting. So what you can do is basically you can change the time of your load consumption. Instead of morning, you may consume the same load in the evening or vice versa.
Okay, that means load shifting is a good one,
Yes, load
more
shifting is
reliable.
more reliable. Now, which demand side management strategy is used in DC microgrid to reduce the peak demand in AC system? So, among peak clipping and load shifting, we saw that load shifting was more favorable, right?
Yes, yes.
And so here also these loads are DC and AC type. So if you basically shift the DC loads, then the overall load will also be decreased. So that is your load shifting. Then is Yes. So
Hello.
next, hello, yes. Next
Yeah,
is,
confidential.
hmm,
All all load profile we can publish. No any confidentiality.
yeah. So, although, as you said, all load profiles are confidential, but among this, the most sensitive one can be for industrial because there you have money involved, right? So that's why we say that this industrial type of consumers, they never want to share their data because they have profits related to those.
Okay, okay. In that sense.
Yes. Now, okay, so it is asking the full form of HEMS. So whether it is home energy management system, house energy management system, a residential energy management system, or consumer energy management system.
Ma'am, slide is not clear. DR program applied on
So it is basically asking that which are named as HEMS.
HEMS.
Hmm.
Okay,
Whether
home
it is
house.
home energy management, house energy management, residential energy management, or consumer energy management.
Home energy management.
Yes, it is home energy management. Now, regarding PMU, which is correct, it's limited by economic constraints. Critical buses are prioritized for close monitoring.
Both.
Yes, correct. Again, this is not visible. Which one of the following is robust? I think I will move to the next. I will update it into the slides when I post it
Okay.
in the drive.
Okay, okay. This I think too.
This is correct, I
Disadvantage
think.
of
Hmm.
site. All of the above.
Yeah, correct. It is all of the above. Which of the following is an indication of the real-time balance between demand and power system? Frequency,
Real
real.
power.
Power balance will be for frequency, right? Power PG equal to PB. By matching the active power, basically it will indicate the frequency of the system. We ensure
No,
that it is
not
a
power.
clear.
Real power.
No, it is the directly, if you match this, then it is directly giving you. It is not like an indication, but for indicating this power, real power matching, it will be frequency.
Frequency only. Not real. Indirectly, it is frequency. Okay.
Mhm.
Okay. Thank you.
Thank you. So it is basically asking that whether PV array can or cannot provide inertia. So again, PV are renewable. You have only a panel. There is no like machinery part. So PV cannot provide inertia to you.
But wind, you told that is induction machine is machine. That is
Yes,
why it is inertia.
yes,
Oh,
yes,
in that sense, we have to evaluate.
yes. Where what component you are using with the because in PV you have the generator connected with you.
That
In the
means
wind.
PV having no, yeah,
Hmm,
wind having machine.
hmm. So because wind you have this AC wind is connected with the DFIG and it is directly giving you the AC power. PV panel, you have a converter if you want a DC-DC converter or DC-AC converter, and it is giving you DC power. There is no other thing, only a panel and a converter. This converter is also a powertronic device, like your MOSFET and switches will be there. So no, like rotating mass or rotating part is involved with it. Hence, it will no cannot store energy in those parts.
And that means we can say here like this PV array provide active power, but there is no not supporting any inertia.
Yes, yes, correct, correct.
that giving active power, but not supporting inertia.
Yes.
That one, fourth one.
I think it is not visible, but what you said is correct.
PV array provides neither. No, I think third one. It is not clear.
So, I will update this while uploading this slide.
Okay, thank you, ma'am.
So, what are the different demand side management strategies?
All of the above.
Yes, correct. Sorry. Next is percentage reduction in inertia region wise. So, it is a data based question again. Because of this
Percentage of
renewables,
reduction.
the inertia is decreasing. So, how much decreased?
And that means why adding more RES, then inertia is decreasing.
Yes, because you're replacing the synchronous generator with the renewable energy resources.
Yes, yes. The percentage of reduction in inertia constrained region, which is that
It
is
is a
database. I don't know.
database. It is actually in European countries, European Union, it is 25% decrease. So huge decrease in
That
inertia.
that means they are more depends upon now RES.
Yes, they have greater RES penetration, it will imply.
Okay, okay.
Um, I think again I will update this. It is not visible.
Hmm. Which following
Which
are
of
the
the
list of
following do not have both active power control capability for grid stability?
PV array, battery storage.
Battery storage will have, we have stored energy there, right? PV array, basically you can not control the power that is coming from the sun. If you have a battery with it, then only you can control how much power you want to inject. Otherwise, it is uncontrolled.
That means PV array we cannot control.
No, no. If you have that any control algorithm like your MPPT, something like that, or you have a storage with that, then only you can do that.
But the inverter we cannot do anything.
No, in battery you have the stored energy, so it is in your hand whether to charge or discharge, right?
Okay, okay, okay.
Mm.
Uh, okay, in that sense, okay, we have to think on that way.
Yes,
Then
sir.
we already discussed one previous one one case. Then we can correct that sentence is like this: PV array provide neither inertia nor active power control support
Yes,
on based on our now discussion.
yes, sir. I will update that. That was not visible, so I'll update that while
Yeah,
uploading.
yeah, yeah. That means I thought maybe inertia only. There is no any rotating machine. That's why inertia is 100% not supporting. But as per our this question, we PV array have there is no any active power control also too.
Yes, sir.
Thank you.
Okay.
Mhm.
I think it brings us to the end of the lecture. If you have any doubt, you can ask or we'll close for this week.
Okay, and no any doubt, ma'am.
Okay. Thank you. Thank you for joining. We'll meet in the next week for week 9 discussion.
You are research holder in IIT.
Yes, sir.
Okay, okay. What is your field? Smart grid or any other subjects?
This power system engineering only. So I work
Power
for system operations and energy markets.
energy markets. Okay. IIT Kanpur or
Roorkee, sir.
Roorkee? Roorkee. Okay, ma'am. Next
Okay.
next week we can meet. Okay. Thank you,
Thank you.
ma'am.
Thank you, sir.